Now we will extend our understanding to the concept of capacitance. Capacitance is the ratio of the change in an electric charge in a system to the corresponding change in its electrical potential. It is used to describe the functioning of capacitors, which store charge usually on two separate conductors, and its value is a function of the capacitor's geometry, the distance between the conductors, their size, and construction. The formula for capacitance is C equals Q divided by V, where Q is the magnitude of the charge stored on each conductor, and V is the voltage applied to the plates. A common example is the parallel plate capacitor, with two rectangular surfaces of opposing charge of area A, a distance d apart, separated by a dielectric medium. In order to find this capacitor's capacitance, we must determine its voltage in terms of its geometry. We can start, as with the spherical example, by finding the electric field within this capacitor by placing a Gaussian surface between the plates and setting up our equations. It is clear that all the field lines running from positive charge to negative charge are normal to the surface. Because the field is constant across the distance d, our integration to find the voltage difference just becomes multiplication with the electric field vector. Now that we have the voltage in terms of the capacitor geometry, we then substitute into our formula for capacitance. Here we confirm that the capacitance of a parallel plate capacitor increases with its plate area A and decreases with its plate-to-plate distance d. We can find the voltage geometry relationship for other types of capacitors in a similar way. In order to do this with wires, we need to analyze the voltage difference about a cylinder. Consider a cylinder of length L with 2 points D1 and D2 positioned above its surface. Note that the location of these points along the line or their radial offset have no bearing on their difference in potential. To find the difference in potential between these two, we again start by finding the electric field of the wire, then setting up our equation. We set our Gaussian surface to be about the wire. In this case, our Gaussian surface area is therefore a function of the cylinder radius r, akin to our earlier spherical example. So our electric field becomes capital Q on 2 pi RL times epsilon naught. In order to get rid of this length L, we consider the charge capital Q to be uniformly distributed along the wire with a unit length charge of lowercase q. That is, capital Q equals lowercase q times L. We can therefore substitute this unit length charge into our equation for the electric field. Finally, we integrate the electric field with respect to r between the points D1 and D2 to find the equation linking potential difference and geometry. Our equation verifies to us that the potential difference is purely a function of the point's relative distance from the cylinder. Note that both D1 and D2 rest on equal potential contours about the wire. We'll now use this equation to determine the capacitance of a two-wire system. Firstly, we'll write our equation for capacitance again. For a two-wire transmission line, we can calculate the capacitance between the two by assessing the voltage between two very long cylindrical conductors. Consider two lines separated by distance d, one with positive charge and the other with negative charge, so that the electric field points towards the latter. The voltage between conductor 1 and conductor 2 with respect to Q1 will take the form we just described before, this time denoting charge Q1 and the distance ratio being d on r. As we are again assuming wires of equal radius, the voltage from conductor 2 to conductor 1 with respect to Q2 is the same, but now with charge Q2. We know that these voltage drops are equal and opposite by looking at our model, so we can rewrite the first equation in terms of Q2. Now using the principle of superposition, that is, the potential differences over the same space sum arithmetically, we can determine the voltage difference due to the presence of both charges. We can further simplify this by understanding that the first charge is equal to the opposite of the second charge. Finally, substituting into our capacitor equation, we get an equation for the capacitance between two wires equaling pi times epsilon naught over the natural log of d on r farads per meter.